All right, welcome back. So I haven't talked yet about the second derivative test in multiple dimensions. So let's do that now, okay? So remember our second derivative test. That said that if you had y equals f of x, f double prime of x less than 0, you had a local max. No, local, yes, max. F double prime of x greater than 0, local min. F double prime of x equals 0. Remember, this is also where f prime of x has to equal 0. Then if it equals 0, then the second derivative test fails. Okay, so there is a multiple dimensional version of it. I use it much less now than I used to because I just don't use it that often, but it still has use. So let's do it. Okay. So what we're going to look at is we're going to look at the second derivative matrix, or the Hessian matrix it's called. Or maybe the Hessian is the name for the determinant. I can't remember exactly. But if you look up, if you Google Hessian and matrix, you'll find exactly this stuff. Okay. I'm going to write it like so. That's the second derivative of, say, x and y. And what that is um, make a partial with respect to f of x squared, partial with respect to f of x, and then y. I can't remember which order is which, but it doesn't matter because for reasonable functions, these two things are the same, right? Okay, for reasonable functions, those two things are the same. Okay, and you might see it written like so. No. Okay. So I always have like confusion which way, but sort of the way I think about this is taking the derivative with respect to y and then taking the derivative of that with respect to x, which means this and this become the same thing. I'm not sure if that's right. Like I said, for anything that's reasonable, these are the same anyway, so it doesn't matter. Okay? And then the determinant of that we'll write it like so. This is what we test. Okay, so now this, if it's greater than 0 and those two things are both greater than 0, then we have a local min. I always have to remember, I think about y equals x squared as my example that has a local min, and the second derivative is 2. So I just sort of always remember, okay, greater than 0, boop, local min. Okay? If it's less than 0, and we're still going to have, now we're going to have f, oh, sorry, this is still going to be greater than 0, but now if these two things are less than 0, we have a local max. Okay. Now, if this thing actually is less than 0, if this is less than 0, then what happens is one of these has to be positive and the other has to be negative. So that means we get what's called a saddle. Likewise, if this whole thing is greater than 0, both of these have to be the same sign. Okay, they either are both positive and you have a local min, or they're both negative and you have a local max. That's if this is positive. Okay, think about it, because this is always positive. Okay, so if this is less than 0, okay, then you get what's called a saddle point. And what that means is one of them is going to be positive, one is going to be negative. I know, but fxy squared, you can show that this is going to always be less than the product of those two, in magnitude at least. Okay? Okay, so that's a saddle point. Okay? And if this is equal to 0, then your second derivative test fails. Okay, so let's take a look sort of at like the prototypical or canonical examples. Make this a little smaller. Okay, so let's take a look at this example first. Okay, so sort of the typical example to think about is the one we actually started the day with. F of xy equals x squared plus y squared. Okay, in this case, f2 of xy, the second derivative is going to be 2, 0, 0, 2. Okay, and our graph looks effectively like so, right? Okay, so we have this minimum at the bottom. Okay. Let's take a look at this example. This example is not much different, to be honest. In this example, okay, our second derivative matrix oh, I haven't given you an example, have I? The f of xy that I want to use is negative x squared minus y squared. Okay, so in this example, the second derivative is negative 2, 0, 0, negative 2. And the graph, very similar, but now it goes down. Okay, and you have a nice little top there. Okay. All right, we'll go to the next page. We're going to look at both of these here. You can probably guess what this example or the canonical example is going to be. This example is going to be, so let's take f of xy equals x squared minus y squared. Okay, so in this case, the second derivative is 2, 0, 0, negative 2. Okay, and our graph okay, it looks like so. X squared is going to go up. So, and the y squared is going to go like so. And this is a typical example of what we call a saddle point. Okay. All right. All right, I want you guys to pause the video for a second after I tell you what to do. Okay, did you pause it? No, because I have to tell you what to do first. I want you to see if you can guess what this looks like. Okay, so just pause the video for 5 seconds. Okay, if you're back now, let me give you the graph. So the idea here is the typical example here is going to be f of xy equals x squared. So it's actually going to be just the curve in only x squared. It's like a cylinder type thing, right? Remember we talked about cylinders before. It just has that one dependence, even though it's a three-dimensional graph. Okay, so let's look at what that means. Let's see what that. So if you had said y squared, that would have also been valid. Okay, so and then it just keeps looking like that all the way through. Okay, so it doesn't really change in a y at all. Actually, I don't like the way this looks. Let's try that again. That looks better. Okay, so it's kind of like just a sheet in the y direction. Okay, it's actually constant in y. Okay, that's really nice actually. Okay, let's take that second derivative. Two, zero, zero, zero. Okay, so you can see that as you travel along y, there's no change in what's going on. It's not changing at all. It's just straight there. But you do have stuff going on here. So second derivative test doesn't really give you anything there. Okay? All right. All right. I will see you in the next set of video, or the next video.